Okay guys, so now that we talked about the basics of exponential functions, we're going to talk about exponential growth and decay. So the first thing we're going to start with exponential growth, okay? So here's the equation for exponential growth. I really want you to go ahead and write it down right here. I just highlighted it in green. So this is exponential growth. Okay, the A stands for the initial value, whatever it may be. Your R is your rate, and usually X is your time. Okay, notice it is very similar to what we've been doing, but now we're going to have specifics with it. So exponential growth is this green one. Okay, you're going to start it. Make sure you pause the video, write that down. And you also want to signify what each thing means. So A is your initial value, R is your rate, X is your time. Okay, so an example of this, it says the population of Hillville grows at an annual rate of 15%. What will the estimated population of Hillville be in 5 years? So if you look over here, they give us the initial population of Hillville to be 5,000 people. So our equation, right, is A times 1 plus R to the X. Okay? Well, our A is going to be 5,000 people. Our R is 15%. However, we always convert the percent to a decimal, so we're not going to use 15%. Instead, you think about it, the decimal's right here on the right. I want to move it 2 to the left to make it a decimal, so I'm going to use 0.15 as my R. All right, and I think that's probably the hardest part when we do growth and decay is you got to convert the percentage to a decimal, so you always move it 2 to the left. And then the last thing is going to be your time, which in this case is 5 years, so that's my X. So now we just plug it all in. So I do 5,000, 1 plus 0.15 raised to the 5th power. So I would do the parentheses first, follow in order of operations. So I would take 1 plus 0.15. I get 1.15. And then I'm going to use my calculator to raise it to the 5th power. Press enter, and I just leave it as that weird long decimal. So you should have got 2.011357188 if you're following along. And typing this into your calculator, which you should. This will definitely help you. And then I'm going to multiply by 5,000. So in 5 years, we think the population will be 10,000. And we'll round up to the nearest whole number. It was 56.78, but we'll round out to 10,057 people, right? Because you're not going to have half a person. Okay? So that is how you use exponential growth to help you solve what you think the population will be in 5,000 years. The next one, it says the population of Valley Town is also 5,000 with an annual increase of 1,000. Can the expected population for Valley Town be modeled with an exponential growth function? So if I'm annually increasing by 1,000, right? 5,000 is my initial value, but annually increasing means I'm going up 1,000 every year. We don't know the number of years. Okay? It says, can we use this to represent an exponential growth function? Well, we don't use this as an exponential growth function because they don't give us a rate of increase. You see, the annual increase is 1,000, right? Which means we're going up by 1,000 every single year. So we're adding 1,000 every single year. So that's a linear function. Okay? It's not an exponential function. But that's why it's different than exponential. Okay? So then we have exponential decay. Again, very similar, right? We're still using the a times b to the x. However, exponential decay looks like this. Very similar to the growth, except for instead of adding r, I'm going to subtract r. So same thing. Your a is still your initial amount. Your x is usually your time. And your r is a rate percentage converted to a decimal. So it says a video is labeled a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. The number of views decreases by 25% each day after that. In how many days will the video stop being a fan favorite? So we're going to figure out how many days will it be below 1,000 views. Well, we already know after 3 days, it's going to be at 3,456, right? So if you look at my chart over here, it looks like we could try 6 days and see what that gives us. Okay, our initial value is that 8,192 views. Our time was 6 days, and our R is 25%. Remember, we don't use percentage, though. We use a decimal. So now I'm going to plug everything in. So our growth function is the initial times 1 minus, because that means decay, minus instead of plus, and then raised to the 6th power. So I would do 1 minus 0.25, raise it to the 6th power, and then multiply by 8,192. So when I do 6, I get 1,458 views. Well, is that below 1,000 views per day? No. So let's keep going. Instead of 6 days, we use the same equation. But now instead of 6 as our time, we're going to try, let's try 7 days. See what that does. Well, I get 1,093.5 views. Still not below 1,000, so then we keep going. Let's try 8 days. 8 days is probably going to work, right? But again, we want to double check. So we're going to plug it in. And I get 820 views on that day. So now it's below 1,000. So how many days will the video stop? How many days total will the video stop being a fan favorite? Well, in 8 days, it will stop being a fan favorite because it was decreasing by 25% each day. Okay? So video is labeled a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. Suppose the number of views decreases by 20% per day. In how many days will the number of views per day be less than 1,000? Well, you think about it, if it was decreasing by 25%, it took 8 days. So it's probably going to take more than 8 days. So I want you to try this one by yourself. Pause the video and see if you can figure out how many days it will take. So if I do this one, instead of 8 days, I'm going to start at 9 days and just see what that gives me. So my initial amount times my 1 minus, this is 0.2 instead of 0.25. I'm going to raise it to the 9th power. So we're going to try 9 days. Well, 9 days, I still have 1,099 views. So that one doesn't work. So now let's try 10 days. Well, 10 days gives me 879 views. So, because it's decreasing at a smaller rate, smaller percentage, it's going to take longer. So this one takes 10 days to get to where it's not a fan favorite anymore, instead of 8 days like the one above. And hopefully that's what you got whenever you were doing this. Okay? So it says the number of pica in a region is decreasing. How does a decrease in the pica population for years 1 to 5 compare to the population for years 6 to 10? Well, if you think about it, say I have a graph that looks like this, right? So that means decay. Okay, I'm going down. Years 1 to 5, well, year 1 is going to be right here. Year 5 is going to be right here. Year 6 is going to be somewhere in here. And year 10. Which one has a sharper decrease? Hopefully you're saying years 1 to 5 have a sharper increase. So we're not really doing like any math, plugging in any equations or anything on this one. We're just talking about how much does it decrease? Well, from 1 to 5, it's going to decrease a lot more than it does from 6 to 10. So years 1 to 5 have a bigger decrease than years 6 to 10. Now, before we do this last one, there's one other thing that you guys need to know, and that's going to be the compound interest formula. So I want you to go ahead and write all this stuff down. Compound interest is this formula right here. You also need to know what everything represents. So A is the amount paid, P is your principal amount, R is your rate of interest, N is the number of times per year it is compounded, and T is the time in years. All right, just so you know, N is this kind of a special thing here. They use some different terms here. So if I say annually, that's going to be my N is a 1. If I say biannually, my N is a 2. If I say quarterly, my N is a 4. If I say monthly, my N is a 12. And if I say yearly or daily, daily, my N is 365. Okay, but most of the time it's going to be these top 4. Okay? So you need to know what those key terms mean. So annually means 1, biannually means 2, quarterly means 4, monthly means 12. So then they give you some equations. So it says, or problems. Kimberly's family invested in a certificate of deposit for her when she was born. The interest is compounded quarterly. That's a key word. Quarterly. That means my N is going to be a 4. So it says, what is the value of the CD at the end of 5 years? So the amount deposited, which is my A, or my P, that I like to write down. So I'm going to write everything down. So my P is a 3,000. My R, my annual interest rate is 8%. My N, we just talked about, is 4. And the last thing I need is my time, which is 5 years. So now we're plugging it into this formula. So replace the P with 3,000. 1 plus my rate, it has to be a decimal still, so 0.04 divided by, or 0.08 divided by 4. And then 4 times 5 gives me my exponent. So if I simplify it, it all looks like this. 3,000, 1 plus 0.02 raised to the 20th power. So just like what we did before, you're going to type it into your calculator. 1 plus 0.02 raised to the 20th power. Press enter. You should get 1.485947396. And I'm going to multiply that by 3,000 to get $4,457.84. So that's how much their certificate of deposit is going to be in 5 years. So then it says B, will the value of Kimberly's CD be greater after 15 years if it is compounded annually rather than quarterly? So now we need to do this twice. So annually, we're still kind of using the same rates here. We don't really have to change any of that stuff until we get to our compound interest rate. So annually means I'm going to divide by 1. So I'm going to say 0.08 divided by 1 times 1 to the 15th. Quarterly, this one in a different color. Quarterly means I'm going to take 3,000 times 1 plus 0.08 divided by 4 raised to the 15 times 4. So then we would solve them both. So I would do first one in purple. I'm going to do 0.08 divided by 1, and I'm going to add 1 to it. Now 1 times 15 is 15, so I'm going to raise it to the 15th power, and then I'm going to multiply by 3,000. So you should get $9,516.51. Now if I do the other one, I'll do 0.08 divided by 4, add 1, raise it to the 60th power, because 15 times 4 is 60, and then multiply by 3,000. I get 9,843.09. Well, which one's worth more money? hopefully you're sitting there saying, well, quarterly I make $300 more. So compounded quarterly is a lot more than compounded annually. Okay? And then lastly, it says, what will be the difference after 15 years if the CD is compounded semi-annually rather than quarterly? So we're going to take that 3,000. Semi-annually means I'm going to take my rate and I'm going to divide it by 2. So we do 0.08 divided by 2 plus 1 times 3,000. Sorry. 0.08 divided by 2 plus 1 raised to the 30th power times 3,000. So then it wants to know the difference. Well, I would take my quarterly answer, which is the black one, and subtract the red answer, which is the red one. And you kind of look at it, you're going to make $13 more dollars. So that would be the difference if you did it quarterly rather than semi-annually. And then lastly, it says monthly. So I would take 3,000, 1 plus 0.08 divided by 12. 12 times 15. 12 times 15 is a big old number. We'll do that one first. So I know 12 times 15 is 180. So I'm going to do 0.08 divided by 12 plus 1 raised to the 180th power times 3,000. And I get 9,920.76. So you make more money if you do it monthly than if you do it quarterly. Again, guys, the equations don't really change a whole lot except for your ends usually change, or your time depending on the years they want to give you. Okay? So that's compound interest. And then lastly, there's one problem that I kind of like to go over. It says, Rich is comparing the cost of maintaining his car with the appreciating value of the car. When will the cost and the value be the same? Well, this one says it starts at $20,000 and decreases by 15% per year. So that's a decay problem, right? So we're going to say 20,000 times 1 minus 0.15 raised to the x power. Okay, the maintenance equation, it says the first year it costs $500 and then it increases by 28% per year. So we're going to say 500 times 1 plus, because that's a growth, because I'm increasing, looking for those key words, 0.28 to the x. Well, we don't know the time, right? It says when will the cost and the value be the same? So what we're going to do is we're going to take those two equations and we're going to type them in on Desmos just to kind of see what it'll look like. So we're going to take 20,000 times 1 minus 0.15 raised to the x. Zoom out. There's my graph of that one. So then we're going to take 500 times 1 plus 0.28 to the x, which is what we did over here. Okay? So then as I go up, kind of notice they're getting closer together, right? So I keep going up, keep going up, keep going up. They eventually are going to cross. Kind of went past it on that one. So if you think about it, about 9 years, they're pretty much the same, right? They kind of become one line. So it says, when will the cost and value be the same? We're going to say about 9 years. So like this one's kind of another exact, we don't need an exact answer. There's not any homework questions over this one, but it's nice to talk about a real life problem that you might see. But again, growth and decay are the main things, and then compound interest is also pretty important for this lesson. So if you guys have any questions over those three formulas, I'm not really worried about that last one. I'm more worried about, can you do this, exponential growth? Can you do exponential decay? And then can you do compound interest? Okay? So if you have any questions over it, make sure you guys reach out. Your homework will be a Pearson assignment. Make sure you get that done, and then we will see you next time. So have a great day.